Everyone, welcome back. This is problem number 25 in this AP Physics C Mechanics multiple choice test. This is the second problem in this set of three relating to this situation. Two satellites of masses m1 and m2 orbit a planet of mass m in circular orbits. The satellites travel in opposite directions with speeds v1 and v2. Their orbital radii are r1 and r2. Assume that m, which is, I'm going to write it as MP, mass of the planet, is going to be much greater than the mass of M2, which is greater than the mass of M1. And problem 25 asks us, the magnitude of the angular momentum of the two satellite system is best represented by, and our options are A, the absolute value of M1v1 plus M2v2, B, the absolute value of M1v1 minus M2v2, C, the absolute value of M1v1 R1 plus M2v2 R2, D, the absolute value of M1v1 R1 minus M2v2 R2, and E, the absolute value of M1v1 over R1 plus M2v2 over R2. So what this problem is dealing with is angular momentum. There are going to be a couple sub concepts that we're going to talk about, but angular momentum is the big one. So angular momentum is represented by L. It is equal to I, moment of inertia, times omega, which is angular velocity. So we're actually going to break this down into talking about moment of inertia and angular velocity. So moment of inertia is basically the rotational equivalent of mass in terms of like force. This equation is basically the Newton's second law, but angular. So instead of being force equals mass times, excuse me, no, that's the torque equation. This is just the momentum equation, but angular. So instead of being p, which is the linear momentum variable, is equal to mv, it's going to be L is equal to I omega. So here I represents how resistant the mass is to movement, to rotation. So for this mass, we're going to use mr squared. Different objects have different moments of inertia, but unless it tells us otherwise, we're going to use mr squared. That's like the basic one that's used for point masses. And although these satellites, it doesn't really tell us what they are, we're just going to assume that they're point masses because it doesn't give us any other information. And now omega. So velocity is equal to radius times omega. So that means omega is going to be equal to velocity over r. Now we're just going to plug both of these in for I and omega. So L is equal to first I, mr squared, second omega, which is v over r. Now we can cancel some things out. This r squared is going to cancel out, and we're going to be left with L is equal to mrv. Now, this is great. This gives us the angular momentum, but we're going to have to, this is asking for the entire system. So these two satellites, we're going to have to figure out the angular momentum for each. But good thing it's pretty easy. We can pop the subscripts in, and it actually works out like that. So that's angular momentum 1. Angular momentum 2, as you can guess, it has all the exact same variables, so it's just going to be mass 2, radius 2 times velocity 2. So now let's sum all of the angular momentum in the system. It's going to be equal to L1 plus L2, which is going to equal M1 R1 V1 plus M2 R2 V2, and it's asking for magnitude. Magnitude lets us know that if it is negative, we want to make it positive. So that just means we get to pop in the absolute values here, and then let's see what our answer matches up with. Nope, this does not have the R1 and R2. Nope. Here, yep, this looks right. C is our answer. D, this should be addition instead of subtraction. Here, I don't know why they're dividing by r instead of multiplying by it. But that is our answer. Using angular momentum with the equation for moment of inertia, and the equation for velocity in terms of r and angular velocity, which is omega. So thank you for watching. Let me know if you have any comments, questions, suggestions, if you're confused about any of this. Good luck studying for the test, and our next problem is going to be 26, the last in this set of 3. Thank you for watching.